This is part 2 of lecture 1.3 of Math 108, Logical Equivalence. In this video, we will give some basic logical equivalences and use these to obtain other equivalences. Let P, Q, and R be unknown propositions. The negation of a proposition P is P. This is the double negation law. The disjunction P or Q is equivalent to the disjunction Q or P, and the conjunction P and Q is equivalent to the conjunction Q and P. These are the commutative laws. The statement either P or either Q or R is equivalent to the statement either P or Q or R. The statement P and both Q and R is equivalent to the statement both P and Q and R. These are the associative laws. In each of these cases, we may write the propositional form without grouping symbols. The statement either P or both Q and R is equivalent to the statement either P or Q and either P or R. The statement P and either Q or R is equivalent to either both P and Q or both P and R. These are the distributive laws. Note that in these cases, the grouping symbols are required. The negation of the disjunction P or Q is not P and not Q. The negation of the conjunction P and Q is either not P or not Q. These are De Morgan's laws. Each of these equivalences can be proved by showing that the truth tables of each pair of propositional forms are the same. This is left as an exercise. Here are more equivalences which involve conditionals. The sentence P implies Q is equivalent to its contrapositive not Q implies not P. We showed this using truth tables in an earlier example. The sentence P implies Q is equivalent to either not P or Q. The negation of the sentence P implies Q is equivalent to P and not Q. The biconditional P if and only if Q is equivalent to P implies Q and Q implies P. The proof is again left as an exercise. Observe that items 3 and 4 follow from the definitions of P implies Q and of P if and only if Q, respectively. We shall also use the following properties of logical equivalence. First, any propositional form is equivalent to itself. Second, if P is equivalent to Q, then Q is equivalent to P. And third, if P is equivalent to Q and Q is equivalent to R, then P is equivalent to R. These theorems allow us to determine if two propositional forms are equivalent even without using truth tables. For instance, let us consider the propositions not both P and Q, P implies not Q, and Q implies not P. Not both P and Q is equivalent to either not P or not Q by one of De Morgan's laws. This is equivalent to P implies not Q by the result which says that P implies Q is equivalent to either not P or Q. Here we replace Q with not Q. So not both P and Q is equivalent to P implies not Q. P implies not Q is in turn equivalent to its contrapositive, which is the negation of Q implies not P. By the double negation law, the negation of Q is Q. So this is equivalent to Q implies not P. This proves the equivalence of all three propositional forms. To illustrate, suppose that P is the proposition 2 is rational and Q is the proposition the square root of 2 is rational. The sentence, it is not the case that both 2 and the square root of 2 are rational, is the proposition not both P and Q. This is equivalent to the sentence, either 2 is not rational or the square root of 2 is not rational, which is the proposition either not P or not Q. And to the sentence, if 2 is rational, then the square root of 2 is not rational, which is the proposition P implies not Q. And to the sentence, if the square root of 2 is rational, then 2 is not rational, which is the proposition Q implies not P. In this next example, we show that P implies both Q and R is equivalent to P implies Q and P implies R. We can write the conditional P implies both Q and R as the disjunction either not P or both Q and R. By the distributive law, this is equivalent to either not P or Q and either not P or R. Either not P or Q is equivalent to P implies Q, and either not P or R is equivalent to P implies R. This proves the equivalence. To illustrate, suppose that P is the sentence, the square root of 2 is rational, Q is the sentence, 4 is prime, and R is the sentence, 7 is odd. The sentence, if the square root of 2 is rational, then 4 is prime and 7 is odd, is the statement P implies both Q and R. This is equivalent to the sentence, the square root of 2 is rational implies that 4 is prime, and the square root of 2 is rational implies that 7 is odd, which is the statement P implies Q and P implies R. Observe that in the first statement, we use a comma before the word then to indicate that the consequent of the conditional is the entire statement 4 is prime and 7 is odd. In the second statement, we use a comma before the word and to indicate that the two statements in the conjunction are the sentence the square root of 2 is rational implies that 4 is prime, and the sentence the square root of 2 is rational implies that 7 is odd. You have come to the end of lecture 1.3. Before you proceed to lecture 1.4, you are strongly encouraged to do the exercises given at the end of these slides. Thank you for your attention.